to our presentation on our research paper titled Graph Neural Network Deep Dive into Successful Counterattacks. My name is Joris, this is Amod. Before we get started, I want to point out the QR code on the slide. It will be on a couple more slides. If you scan it, you'll get access to the data and the code that we used for our research project. It's also on a couple more slides, so if you don't catch it, you can catch it somewhere during the presentation. Yeah, like I said, this is Amod. Amod is currently in his last semester at the University of Northeastern University in Boston, where he studies his master in artificial intelligence. And he did a co-op at US Soccer between June and December of last year, and this project is a direct result of that co-op. And my name is Joris Bekkers, and I'm a sports analytics engineer, and I've been working with US Soccer since 2018. So just a brief list of the contents. We'll first talk about what the research is, what data we used. Amod will dive deeper into the methodology and the results. And then I'll touch on some of the potential applications of the research. We'll also touch on some of the limitations of the research, and then we'll end with the conclusions and give the judges some time for questions. All right, so our research revolves around three parts. Gender-specific counterattacking graph neural networks. And we say gender-specific because we wanted to model both men and women, and with the main goal of increasing data availability in women's soccer and increasing the research availability of women's soccer. We looked specifically at counterattacks because we thought it was an interesting subject, and because counterattacks are an important part of the US Soccer Style of Play Guide, and because they're an important part of the game in general. And we modeled these counterattacks using graph neural networks, and we were inspired to use graph neural networks and try out these graph neural networks on tracking data, on soccer-specific tracking data, by a talk that Paul Power gave at the Friends of Tracking YouTube channel back in 2021, where he showed some really cool applications. And with that, I'll hand it over to Amod so he can talk more about what we did.
Sure. Thank you, Joris. So let's dive into the counter-attacking aspect of our project. So we use Opta's on-ball event data to identify counter-attacking sequences. So we used an algorithmic approach to identify our counter-attacks. Now we did that with the help of US women's national team and men's national team performance analysts. So here are some of the rules that you can see on the screen. So we defined that the sequence should start in the defensive half of the pitch. The ball should move at least 10 meters forward. It should have a velocity of more than 4 meters per second. And most importantly, we defined that the last event should occur within that ellipse, just to avoid any long balls or potential moves that do not really count as counterattacks. And then how do we define a successful counterattack? Now, in our project, we define that any pass of a sequence that enters the 18-yard box, which is highlighted in the red, is a successful counterattack. And we kind of do that just to have enough data to model our graph neural networks, because if we do decide to use something like goals or shots, then we don't really have enough data to kind of model that. Moving on, let's talk about the gender-specific aspect of it. So we use skill corners tracking data from the MLS and NWSL for the men's game and women's game respectively. As you can see from this chart, we have fewer samples for the women's frames and more for the men's. It's almost a 4:1 ratio. And then we also built a combined model which includes all of the data for men and women. And it is important to note that we used a 50-50 split. So there are 50% of successful counterattacks in the data set and 50% of unsuccessful counterattacks. Okay, so let's talk about the graph neural networks. And before touching on graph neural networks, we've seen some projects of iteration that use convolutional neural networks. Convolutional neural networks use an image-based representation of a single frame. The drawback with that is that it only encodes the location. But with graph neural networks, you have these node features, your edge features, and the adjacency matrix. And in that, you can encode a lot of information, such as their velocity, their acceleration, the distance to the goal, and from the ball, which I think is really important. The edge features is a relationship between your nodes, and then the adjacency matrix is a representation of how your graph is. So as you can see in this particular slide, we've connected all the defensive players, all the attacking players, and all of them are connected through the ball. Let's talk about the architecture more in detail. As you can see, these are the graph frames that we have. We pass them through a crystal convolutional layer, which is a graph convolution layer from the spectral package, then through a global average pooling layer, a dense layer, a dropout layer, and finally a sigmoid layer. Now the output that you get is a value between 0 and 1, 1 being how close you are to successful counterattack, and 0 being that you are not probably going to have a successful counterattack. Let's talk about the results that we had. So we observed that the gender-specific models perform better with fewer samples. We got a log loss of 0.48 for the women's model and 0.51 for the men's model. We had a baseline split of 50-50, and we kind of achieved to beat that target score of 0.69 and the ROC-AUC of 0.50. Also, as you can see, for the women's model, we trained it on fewer epochs just to make sure that we are not overfitting our data. Talking about the permutation feature importance, we kind of did this as a sanity check just to make sure to see what kind of features affect our model performance. We observed that the node features of velocity and the angle to the goal and to the ball, like in that order, are kind of very important in finding out counterattacks. We also observed that defensive features are more important than attacking features. And also we need to state that we still need to do a bit more research on how do we analyze this. Like, we still don't know whether an increase in velocity in certain situations help your model or whether a decrease in velocity would help. So that's something that we still look a bit into. I'd like to pass it on to Joris again.
All right, let's talk a little bit about some of the potential applications of this research. In the video, you can see that we've modeled one counterattack and computed the probability of success of this counterattack throughout the whole sequence. This is something that you can use to sit down and analyze with your analysts and with your coaches. One thing that would be interesting to add to that is making it interactive. So here you have a screenshot or a screen cap of a tool that you could make an interactive tool where, in this example, we've changed 2 of the velocity vectors of the attacking players shown in yellow, and making these changes increases the chance of successfully getting into the box by 3.8%. And something else that we can do is we can try to measure which players add more value in counterattacks, perhaps by comparing the actual outcomes to the expected outcomes of said counterattacks where the players were involved in. So yeah, that's just a brief overview of some of the applications that we could use this for. Yeah, let's get into the limitations a little bit. One of the most obvious limitations is reaching the penalty area as a measure of success. Now, no defender is just defending the box, they're defending to not concede goals. So we'd rather have scoring a goal as a measure of success. Another potential limitation is the fact that we used an algorithm to identify these counterattacks, because the model might pick up on some of the specific rules that we set. And basically that. And then another limitation that we were not aware of during the writing of the paper was a blog by StatsBomb, which they published in November 2022, in which they made an attempt to make a combined model. They made a gender-specific model, and then for the expected goals model that they were modeling, they also made a gender-aware model, which basically meant that they added a column to their tabular data to indicate if the shot taker was male or female. Now, in hindsight, to us, it was kind of obvious that we should have also tried this, potentially by adding a node feature that indicated if each player was male or female. And so that's something that we definitely want to look into further. Another potential limitation is, like Amod said, is the sample size, especially for the women's model. It's relatively small, so there might be some chance that we're overfitting, and we need to do a more thorough validation of this aspect. All right, so in conclusion, we have shown that we can use graph neural networks to work well with soccer data. We have shown that we can use them to predict the successful or unsuccessful outcome of counterattacks. We've also shown as sort of a sanity check that which features are important. So velocity is important. We know that counterattacks are supposed to be fast, so that makes sense. and the angle to the goal and the angle to the ball are also important in our model. To us, the most important finding of all is that we should strive to add more women's data into our modeling, because generally models are built on mostly men's data just based on data availability. Like, there's a lot more data out there for the men's game. So we've shown that we can use even like smaller samples to get decent results. And one of the benefits of that is having coaches be able to work with the data and the models that for the game that they're actually coaching. So there are some differences, and maybe these models catch up on that, and that will translate onto the pitch, and then everyone can make better decisions based on that. And finally, I'd like to mention that during our research, or rather after our research, we created a bigger data set that we share on our GitHub repository. This data set consists of an imbalanced data set, so 95% unsuccessful counterattacks, and then 5% successful counterattacks, where the actual success is scoring a goal. So the whole sequence is labeled as a goal or as a success if the sequence ended in a goal. And this data set has over 200,000 samples, and they're all already converted into a graph representation, so you can just use it and try to build a nice model. The data set is split 50-50 between men and women. So for anyone that likes a challenge, feel free to go on the GitHub repository, scan the QR code, and do some modeling. So with that, we'd like to end our presentation and hand it over to the judges.
Hello. Nice job, guys.
Thank you.
So the one piece that feels like I'm not quite sure on, if I'm like coaching the women's team or the men's team, and you have like 30 seconds in an elevator, and you want to say, what's the most important thing I can do to implement and win more games? So what's that like 30-second elevator pitch?
For specifically these counterattacks?
Yeah.
I think that's a hard problem, and I think we try to kind of catch that in the application, is that you basically have an infinite search space to find more optimal solutions to your counterattacking. So I would almost say make sure that you can build an environment where you can test out some of your strategies. But I can't say that we found anything that's like a direct impact on the results.
Cool. I appreciate it. Thank you.
Really good job. Thanks. Question about the features. Did you engineer these features, like relative speeds, relative angles, or did you just drop, shouldn't say just, but did you use only X and Ys and let the model sort of discover these features?
No, so we feature engineered these features based on the data. So we had X and Y coordinates as an input, and then you can calculate the velocities and like all the angles between all the players.
And those were the layers and the matrices and the inputs.
Yeah, so you have
one.
you have different features in your inputs, and those are the.
I'm basically just picking your brain here. I'm stealing your stuff. And then what did you use to get the feature importance?
Excuse me?
What tool did you use to generate the feature importance?
Yeah, so I can take that. So for the feature importance, what we did was we changed one feature, like we just looked at the X value, let's say like the horizontal coordinate of the player position, and then we just randomly shuffled it to see the model performance and see how far the prediction was from the original value that we got for that frame. So that's how kind of we get a value that's how far you are from your prediction. And then we did that for all the features, and then the features that gave out the most erroneous value, that's kind of how we decide, oh, this is the most important feature for us.
Awesome, thanks. Last one is, how did you handle offsides events? So I can imagine there could be otherwise very advantageous counterattacks occurring, but you have this millimeter offside call, and that would sort of influence the outcome quite strongly.
Yeah, so the added benefit of using graph neural nets is you can just drop out a node. So when a player is offside, we just drop them out and they don't exist in that situation anymore. So yeah, you'll have one team with 10 until this player is back onside. So
okay.
Just drop out the player.
Thanks.
Great job, guys. Fascinating stuff. I'm going to kind of ask one new question, then piggyback on the previous two questions. So my question, you talk about the choice of Y variable, the success, how you define success of a counterattack, and you mention it also as a limitation. Can you tell us more about the implications of that limitation? So directionality, what is it doing to your model?
So I think I can show this by way of the video. If I can go back there. So if you look at the player on the ball right now, and the closest defender, like they're not defending the box, like this, the blue defender at the top left of the right box, or the bottom left, I should say, they run away. So they're not actually attempting to defend the box right here. They're defending to make sure that they close some space. And so that's a big implication. They're like, no defender will just tackle you because you're trying to get into the box. So I think that's the biggest aspect of that limitation.
So the limitation of your choice of that definition is in your application itself, not so much in the model.
I'm not sure I follow that.
It's in how you manifest it in the application here, right?
Yeah.
In your projection.
Yeah.
Okay. Thank you. That's great.
Right.
And it helps. And then another question. We heard about the guidance that you might give and the feature importance. Can you tell us something about how the feature importance differs between the men and the women and what your insight is there?
Yeah, so if we go to the slides, yeah, so the drop box, the values actually show you, so for the men's, you could see that they have a more feature importance value as compared to the women. So we have like, if we go to and if you read the paper, like we couldn't fit all of those features in this slide, but if you go through the paper, then you would see that there are a lot of sections where we kind of differentiate between the men's and the women's, like the feature importance.
What are the implications? Like, what is the story that we tell that is differ? I see the differences, but like, what is the story there that?
Yeah, so I think that's what we still need to look a bit more into it. As I said, we've not really gone through it. It was more of a sanity check for us at this point in time, and we'd definitely like to go and look further into how we can really identify and what impact can they give us.
Great. Nice job, guys. I really like this slide where you articulated why you used the graph neural net over the convolutional neural net. That was really nice. Two questions. One, I'm going to come back to the success metric. So we've looked at a lot of tracking data in both soccer and basketball. And basketball is much easier because you have a successful event every 30 seconds, and it's very clear what it is. The thing we've struggled with in soccer is defining that success metric. So my first question is, how sensitive are your results to the definition that you picked? Like if I picked a different box, or I say you have to get across this line, are your results robust to that, or will you get a different outcome?
So I expect that we could use the same model to model that, but you obviously get a different outcome because your end target is different.
Mm-hmm.
I think the most important thing is having enough samples to make the model catch on to what you're trying to do. So if you want to, for example, say, well, let's get into the top left corner of the pitch and mark that as a result. If that almost never happens, then like that's an issue. So yeah, that's why we sort of played with getting enough samples to make it usable and make it sort of representative for soccer. So getting it in the box is a good proxy of getting close to scoring.
I see. So if you had more samples, you would make it a tight. Okay, I see. So if you had an infinite number of samples, then your success metric would have been a goal.
Yeah,
okay.
For sure. Yes, that's what we did in the extra data set that we added to the research.
And one more question. So there's been a lot of discussion that I guess two of the differences between the women's game and the men's game is that the motion of the women, it's hypothesized that there's more agility, so there's sort of faster direction changes, although lower total acceleration, and also that the women's game is more collaborative. Do you see any sign of either agility or collaborativeness when you compare the difference in the two games?
I don't think we've seen or looked at anything like that.
Interesting. Thanks.